Hello and welcome to today's video. In today's video, we are going to start a series on acid base theory. So under acid base theory, we want to understand an acid and the base using theories. And here we are going to look at three of those theories or concepts that describe an acid and the base. We have number one, what is known as the Arrhenius theory. We have what is known as the Bronsted-Lowry theory. And lastly, we have what is known as the Lewis theory. So these are the three theories that govern the description of an acid and a base. So without wasting much of the time, we can quickly dive into what is known as the Arrhenius theory. So the Arrhenius theory describes an acid. So look at this in comparison. So Arrhenius theory describes an acid as a substance which, when dissolved in water, produces hydrogen ions. Then describes a base as a substance which, when dissolved in water, produces hydroxide ions. So what this simply means is, if we're going to look at this visually, if we have a substance and we dissolve it in water, so this simply means that if we put an acid in water, so microscopically what we are supposed to see, so microscopically what we are supposed to see is that we should have hydrogen ions contained in that particular solution. Then in terms of a base, so if a base is dissolved in water, according to Arrhenius, microscopically what we are supposed to see is hydroxide ions. We're supposed to see hydroxide ions. So that is his description of what an acid and a base is. Then this theory comes with limitations. So one of the limitations that comes with the Arrhenius theory is that, first of all, it's only applicable, or it only applies to aqueous solution. So for you to know an acid, it means that the solution or the substance that you're dealing with is supposed to dissolve and produce an aqueous solution. That's the only time you can detect whether you have hydrogen ions or you have hydroxide ions. So if that particular substance cannot dissolve and form a solution, then Arrhenius theory is limited. The other limitation, according to the Arrhenius theory, is that it only allows for only one kind of a base, And what we mean is that this can only work for a base that is in hydroxide form. Any form of a base which is different from hydroxide, then we cannot use Arrhenius theory. Then we can introduce Bronsted-Lowry theory. So according to Bronsted-Lowry theory, we're going to look at how an acid is defined in comparison to a base. So here, an acid is defined as a proton donor. Then a base is defined as a proton acceptor. So H positive is known as a proton. So according to Bronsted-Lowry theory, an acid is a proton donor and a base is a proton acceptor. Let me just give a very simple example. So let's look at a reaction that is using the Lewis, a reaction of hydrochloric acid and water. So what this means is that this hydrogen becomes a proton. So when that hydrogen becomes a proton, it moves and attaches itself to that. So this being an acid, it's going to donate. So an acid, in this case, which is hydrochloric acid, is going to donate the hydrogen ion. Then water, in this case representing a base, is going to accept that hydrogen ion. So we're going to end up with something like this, a lone pair there, then positive, then we'll have Cl and negative. So what does this mean? So this, according to Bronsted and Lowry, an acid will donate hydrogen ions. Then a base is going to accept. So when the acid donates a hydrogen ion, it becomes this, and this will be referred to as a conjugate base. So a conjugate base is what an acid becomes when it has lost its proton. Then the water here, which was a base, is going to accept the hydrogen ion to form what we call a conjugate acid. So Bronsted-Lowry theory leads to what we call conjugate acid-base pair. So the acid, when it loses its proton, it becomes a conjugate base. When a base accepts or gains a proton, it becomes a conjugate acid. This leads us to a general equation. So we're going to look at a general equation under the Bronsted-Lowry. So Ha plus H2O at equilibrium produces H3O positive plus A negative. So all these are in aqueous, 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 aqueous. So here we are saying this is an acid, then this is a base. So we are saying when an acid loses, so when an acid loses its proton, it forms what we call a conjugate base. Then when a base, in this case, which was water, gains H positive, it forms what we call a conjugate acid. To look at it from a more visible perspective, let me use, so we're looking at it from this perspective, then water, we have those lone pairs. So we are saying this from an acid will be lost as H positive, which is going to be attracted to this. Therefore, this becomes negative, then that becomes H, O, H, then this is the gained proton. Then it produces something like this. So we are saying this is what is referred to as a conjugate base. So a conjugate base is what is produced when an acid loses its proton number, and then its proton, then this becomes a conjugate acid. So because of the Bronsted and Lowry theory, then there are no limitations in the way we describe an acid, and this can be demonstrated by the following example. So we can have an example of a reaction in gas phase, a reaction in gas phase. So if we were to look at the reaction of NH3 gas plus HCl, both in gaseous state, and producing ammonium chloride, which is a solid. When we look at this reaction, because we do not have, we have the hydrogen ion, but we do not have the hydroxide ion. So in this reaction, according to Arrhenius, this reaction is not acid base, because Arrhenius can only cover for hydroxide and hydrogen. But according to Bronsted and Lowry, this reaction is acid base. What do we mean it's acid base? So it's acid base because there is a donation. So this will donate the H positive, so we'll donate the H positive, and this will accept the H positive. So what does this simply mean? So if we look at it visually, so we are looking at something like this. This is ammonia. Then we have this. So to demonstrate, we are saying to demonstrate the Bronsted-Lowry. So this is an acid, then this is a base. So we are saying the acid will donate the proton. So the acid will donate this proton that will come here. Then ultimately we're going to have this, the new hydrogen, then this. So this becomes positive, then Cl negative. So this, according to Arrhenius theory, it's not an acid base because you're not going to see hydroxide in this equation. But according to Bronsted and Lowry, this is equally a acid base reaction. Why? Because there is H positive donation and then there is H positive reception. So this is what comprises an acid base reaction. To move further, we are going to look at the competition. This is very important. There is need for us to understand the competition of H positive by A and H2O. And I'll give more context to this. So when we look at this general reaction, plus water aqueous, then this gives us H negative aqueous plus H3O positive. So when we look at this reaction, so this is liquid, this is water, it's liquid. So when we look at this reaction, we're going to look at two cases. So I will say case 1 and I will say case 2. So case 1 happens when we have H negative stronger or with a high affinity for H2O. So there are times when this A, remember, this is an acid, this is a base. Then we're saying this is a conjugate base. So we have two bases in the reaction. There is A as a base, then there is water as a base. So in this container, what is happening, maybe before I even talk about case 2, what is happening is in this solution, there is going to be a competition for the proton. The proton that will be produced by this, there will be competition between this conjugate base and the base. So which one is going to react with the produced proton to decide the shift or the position of equilibrium? So this is happening at equilibrium. So if it happens that A has got more affinity for the proton, it means that A will react with the proton, and this means that the reaction will shift to the left. This is at equilibrium. So when this happens, we say that at equilibrium, the reaction shifts to the left. So this favors the production of HA. That is for case 1. Then for case 2, it's the opposite. It's very important for us to understand this relationship. For case 2, we are saying now water, which is our liquid, is stronger than the conjugate base. So when this happens now, the competition between this and water is that water will now react with a proton. So when this happens now, when this water reacts with a proton, it means that the reaction will shift to the right. So we'll say at equilibrium, in this case, the reaction shifts to the right. This favors more of the ions. So meaning more of this and hydronium will be produced. So how is this information important? So we are going to build on this information when we begin to talk about the equilibrium expression, which is normally known as the Ka. So Ka simply means acid dissociation constant. So when we are provided with the general equation, aqueous plus H2O liquid at equilibrium producing this aqueous conjugate base and positive aqueous. To determine the dissociation constant, so we say Ka is given by the concentration of hydronium multiplied by the concentration of a conjugate divided by the concentration of the acid, then the concentration of water. Now, this is where it becomes more interesting. So when we're looking at a hydrated proton, for hydrated proton, we realize that H3 positive, which is hydronium, is equal to H positive. So they can use any of these two, but we usually use H positive to represent the proton. Now, in this solution, we can assure that the concentration of this, which is the concentration of water, so we're looking at this. So the concentration of this water, which is in liquid state, is constant. So when this concentration is constant, we do not include this in the equation because its concentration is constant, remains essentially constant. So the new or the common way of expressing the Ka that you're going to find in most of the books is that Ka is represented as, so remember this is going to be substituted by the H positive, then the conjugate base, then the acid. So we do not include the H2O. So we'll continue in the next video and explain more about the Ka and the dissociation. Thank you and see you.